So thank you for coming back to my talk. So you are not killed. And then I should say the goal, in fact, what I want to show, and I think I almost showed that, but not written yet, some part. It is, so Mn, if Mn has nontrivial circle action, then diff omega of Mn of 0 is perfect. That is the goal of my research for these maybe 20 years. And then yesterday, I showed the Herman theorem. He showed that diff of omega of Mn z, oh no, sorry, Tn 0 is simple. And Monsieur Professor Michel Herman kindly conjectured that so this theorem was in his paper of 1974. He conjectured that the group there is simple. And I think I want you to work on that conjecture, but you don't see how to generalize from torus to all the manifold. And then I said myself that for the infinite group, simplicity implies perfect. And perfect, oh, I should define perfect. So G is perfect. If G coincides with its commutator subgroup. And this is generated by A, B, A inverse, B inverse, the commutator, A, B are in G. So this is a characteristic subgroup of G. And so if G is infinite group, if it is simple, this should always be the normal subgroup, and either it is trivial or G itself. But if it is trivial, it says G is abelian, And yes, please.
Is Herman conjecture known for surfaces aside from torus?
I'm going to tell you, but nothing is known. So it is widely open. We should put in the problem book. Other questions? So I continue. So if it is 0, it means G is abelian, and abelian groups are, in some sense, classified. And the only abelian group which is simple is what we call FP, the finite group of the P element. P is prime. Okay, so if it is infinite group, simple implies perfect. So I want to look at easier question. Then this easier question, even for Tn, it has easier solution. So even for Tn, the fact that diff omega Tn 0 is perfect can be shown only by looking at the Arnold theorem. That is what I said is, so if I take F near the near identity, sufficiently near to the identity, and I take this Diophantine rotation, and if I look at the composition of F with this rotation, and then it can be written as something like this. Okay, this is, I think I explained yesterday. And this implies, of course, F is in fact homologous to R lambda. So G R alpha, G inverse, R alpha inverse. So this part is a commutator, and rotation can be written as one commutator in the product of PSL2R. So this one is a commutator in PSL2R to the n. That thing I almost explained yesterday, and I think it is a little easier because you don't need the first interesting equation. And then second thing, whether I can do some other thing. So for some other manifold, what can I do? And as I said, we have parameterized Arnold theorem. So this one is for only one diffeomorphism, but if we have a family of diffeomorphisms, one parameter or n parameter family of diffeomorphisms, you can also find such lambda and such g. So we can write if f has some parameter, how should I write? Maybe t. And so lambda t and gt are alpha, gt inverse are alpha inverse. And if I only know the proof for the one-dimensional case, so if we only know this theorem for S1, then you can see that that is so for Tn minus 1 family of diffeomorphisms close to identity, if it is such Ft, then this will act in such a way that there is a circle like that, and here you have Tn minus 1 family, and everywhere on each circle you have this Diophantine rotation, and you can use this rotation, and you can find lambda t and gt, and everything is written a parametric way on these circles. Is it clear? I hope. So for Tn minus 1 family of diffuse close to the identity, we have that formula. We have, so this diffeo is, in fact, I should say, so the family of GT defines diffeomorphism of the Tn, and family of R lambda T defines fiber-wise rotation of that manifold. So this one is, in fact, I should say, homologous to this family. So then we think of fiber-wise, orbitwise, maybe PSL2 R action. And in this continuous way, and this thing can be written as a commutator. And this RT is something one commutator. Okay? So it is not so bad, but why we can assume we only looked at the Tn-1 family of the circle diffeomorphisms. It is not all of the diffeomorphisms. But here, if you have one has multifoliation of Mn, so it should be F1, F2, Fk of Mn, such that for any point, Mn tangent plane for these foliations so this is the tangent spaces, a tangent bundle for the leaves, okay? And then this, I wrote not P, but X. Tfk of X is, so it is necessary these things span Mn, and in the multifoliation Tij are transverse. So you can think of, you will put some Riemannian metric on this manifold, and you think of the exponential maps from this tangent plane to the these leaves. Then you will see that for F, diff of Mn close to the identity, F can be written as F1 Fk, such that Fy preserves leaves of Fy. I will draw something. First we go up. It's a kind of easy thing. If you think about 2 torus or something, it is very easy. So in the 2 torus, for example, you have horizontal foliations and you have vertical foliations. So every element of the diffeomorphism send one point to some other point. So these go somewhere, this goes somewhere, this goes somewhere, like this, and like that. Okay? So in some sense, if it is very close to the identity, it will not go far. And then you can just decompose it to this one and this one, horizontal part and vertical part, or vertical part and horizontal part. So the first horizontal thing, of course, preserves the leaves. And the vertical thing, of course, preserves the vertical foliation. So, in fact, this is a proof of that thing. Okay. I hope it is easy. So, yes.
Saying that your diffeomorphism is a composition of vertical and horizontal?
Yes, that's right. Yeah. That is what all I said here. And it is, so if it looks like the coordinate planes, then you think it is obvious, but it may be not commutative. So the decomposition horizontal, yes, right, left, and forward, back, and up, down. So you can decompose if it is three-dimensional in this way. But if you change the order, it will give you some other thing. So it is only necessary that these foliation span the tangent plane. Okay? Yeah. So by using this fact, we can, if you have f of d omega t n 0, and in fact, this is isotopic to the identity, this means. So you will first do the isotopy from identity to f, and f can be very big and complicated, but your isotopy can be cut into the small pieces, and your isotopy from here and there is always near the identity, of course. So first, f can be, maybe I'll put f1, fn, or something. So then these are near identity. And then this Fy is written as Fy1, Fin, and this F1 to F sub 1 and F sub n are just moving in the direction some j's direction. Okay, so Fi j moves in j's direction. Then for this diffeomorphism, I can use that parametric Arnold theorem, and it can be written as a commutator, as a product of commutators. And since everything is written as a product of commutators, we can show that this group is perfect. So this implies diff omega Tn is perfect. I think this proof for the perfectness is a little more conceptual and easier than the proof of the simplicity. I think everyone can prove in this way. But for the simplicity, you have to find the first marvelous equation. Okay? Any questions? So, but here, I said my goal should be if there is one circle action, then I should be able to prove that this is perfect. But as you see, I use at least n for each dimension. I have circle action. I use that, but I can do.
So your positions are analytic?
Yes. If analytic, the decomposition is analytic. If C1, the decomposition is C1. Okay? So this decomposition is really the general thing. Yeah. Yes, please.
Do we assume the circle action to be analytic?
Yes. Surely.
Or maybe it's not something.
This is, yeah, we assume. We can do, I can do the using only one circle actions. Just in some vertical thing. What I want to explain now. So if I have a circle action, so let, I don't know, rho be a circle action on Mn. And then you can look at, of course, always C omega. You can look at the derivative of this action. And this action is generated by some vector field. So let C be a generating vector field. Of rho. Okay. And then, so this is something I have circle action, some vertical thing. And I will, in fact, perturb this circle action. So for any diffeomorphism G of Mn, so G of C, the direct image by this diffeomorphism generates also the circle action, and this should be G O G inverse. There is conjugate actions, and they are generated by sending the vector field there. So at any point, you can find some diffeomorphism is something. If you have this point, I will make this vector field going something like this. Then here, this is two-dimensional. This one, G star QC and original QC spans the tangent plane here, but not here. So I can use also, so in some sense, since G is a diffeomorphism, the perturbed action, the orbit looks like this. And so there are several points where I don't find two vector fields which spans the tangent plane. I will use another diffeomorphism, something like sine and cosine. Up. Not so. But you'll see what I want to say. So for any manifold, I will take G1 to G large N such that C G1 star C, maybe G1 I'll put identity and G2 star C, Gn star C. All of them can span the tangent plane. That means for any point Nx, there is I1 to In such that G1 Gi1 star C at P at X Gin star C spans TXM. Okay. Is it clear? So in that figure, so if you look for the it is easier to look at the singularity. So for the white and red one, you will have some singularity somewhere here. And yellow one and white one, you will have some singularity somewhere here. And for the yellow one and red one, you will have some singularity maybe somewhere here. But these are disjoint in this figure. So for any manifold, you can find, so you will take any point and then find some diffeo such that the image of this vector field should be transversed to the original one and so on. And you can find out of diffeomorphism and make it span the tangent plane. So for example, we want to use only the n diffuse. So I have some figure like this. And here, if we put Riemannian metric on Mn, and then you can define the determinant of C G star Gi, I'm sorry, I1 star C G I N star C. That means at any point you choose I1 and IN, so there is some element of C, such thing there, and then you can look at the volume of this infinitesimal parallelepiped. Then you can define this determinant. And if this determinant is 0, that says these are not linearly independent, and this means it is singularity. Okay? So what I want to do is the same game as here. So it looks, if I am in some diffeomorphism, moving the interior of this foliation, if I have some small diffeomorphism, then it can be make the sum of the composition of two leaf-preserving diffeomorphisms, orbit-preserving diffeomorphism. Okay, but there is some difficulty, of course, at this place. And then, so we see if I have some vector here, we cannot do. Claro. So we have to make as small as possible. So we want to make the diffeomorphism, which is identity along this singularity, and sufficiently flat there. If it is sufficiently flat, we have some hope to write it as a composition of two orbit-preserving diffeomorphisms. All right?
Sufficiently flat means very flat at the contact between the foliations?
Sufficiently flat means, so how can I say? Sufficiently so the jet of the diffeomorphism is that of identity until some large n. This means sufficiently flat along this singularity. So this doesn't move. Yes?
It's it large n was related with the contact of tangency between the foliations.
So this tangency comes from the choice of G1 to Gn.
Yes.
So each choice of these things, you find some tangency. And this is, in fact, represented by this, the determinant function. So what I want to do now is to make it as flat as possible along this singularity. In fact, yeah, this is one point. I have 15 minutes only. Okay. So usually, if you want to work with the diffeomorphisms of the manifold, which is isotopic to the identity, you will decompose this diffeomorphism into the composition of diffeomorphisms whose support is contained in some disk. This is called fragmentation lemma. So, so if you have a diffeomorphism like this, and if you have a partition of unity, which is usual partition of unity is something like this. I'm just drawing. This part is 1, so this is M, and this is 0 and 1. So this height, this height is the partition function, and then in other place, the length between two red things is the element of partition of unity. So this is the infinity case. And using this, you have a mapping. If you have some number, you send the first part to this part, and if the foliation is like that, then the foliation becomes the identity somewhere here, and it only moves. It is almost the same here, but this becomes flatter and flatter. Does this figure make sense for you? Maybe no. So please.
Can you say, I didn't understand. This is, so what is the statement that you're
Yes.
to explain?
So let mi be a partition of unity. And we look at the mu I, which is the sum of mu j, j equal to 1 to I. So this red thing is the graphs of this mu I. And then you will look at the mapping from m cross 0n to m cross I 0, 1, such that so this one is 0 to n. You divide into the n columns, and each thing should go to the difference of nu 0 and nu 1, and nu 1 and nu 2, and nu 2 and nu 3. So this map x t should go to x nu t of nu t and nu t plus 1, I think. And I should put t minus t0, not t0, sorry. And this one is 1 minus t minus t. Oh, I should write visible. T minus t nu t plus 1 minus t minus t nu t plus 1. So that only means it's a level preserving map, and which sends all this one to some figure here. So since this part is width 0, the pullback by this map here is horizontal. This is a C-infinity fragmentation lemma. not convinced. Oh. And then this is fragmentation. And you cannot use it in the real-analytic category. That's the problem. But you can make such kind of the, for example, how can I draw it? If you have, so if this function mu j C omega, so these functions are never, it is positive, but it cannot be identically zero. But as you see, this part, if it becomes only zero or the width zero, it will give you the horizontal leaf. And if you have this zero, at least there you will have one horizontal leaf. And then if this this function is sufficiently flat there, this horizontal leaf, the holonomy is sufficiently flat. So that is the what I call regimentation lemma. And in fact, I will use for mu j equal to coming from these things that depend on some to L. For some L, maybe 1, you will look at the square or the to the fourth power of this determinant, and this will give you the partition of unity, which is real-analytic. And if I use these functions in this machine, then in each diffeomorphism here, which are the pullback of the original diffeomorphism, is flat along the places where this function is zero. So in this way, I can make the diffeomorphism as flat as possible along this singularity. Okay?
Could you say what the statement of the regimentation lemma is?
So this will give you the pullback. Isotopy is so flat along what mu j equal to 0. And then this flat depends on the flatness of this one. Up. Yes?
So do we know, so this partition of unity, do we know what it's subordinate to? What's that? Do you pick a cover first? Or
Yes, yes.
Or you just define those functions and then it gives you the cover?
So that depends on the, you can, you have finitely many positive functions, and then you will look at the sum of everything, those things, and then, so these are the positive functions, and this is the sum of these, and this will give you partition of unity. And I want to do with respect to this function, because this is this measures how transverse they are in the open set. So I want to make the pullback isotopy, for example, k flat along this mu j equal to 0. This is analytic set. So it is not easy thing, but is it clear? No.
Wait, maybe we should thank Takashi and then we go back to the question. I don't know.
Yeah, I will proceed a little more. So I want, sorry. Then with this, I can make the diffeomorphism becomes flat around these things. Then it is also necessary to show something more. So we need what I call the inverse function theorem with singularity. This is only true for the C omega category. So I'm looking at this situation here. And then what we see is along some analytic set, this become linearly dependent. But other places, it is linearly independent. And if the diffeomorphism is sufficiently flat along the set where it is linearly dependent, then it can be decomposed into the orbit-preserving diffeomorphisms. Okay? So the statement of that one is if f is sufficiently flat along and then and of course near identity, then F can be written as Fi1, Fin. So that means what I want you to do. I have singularity somewhere there, but the support, essential things only happens the place where it is transverse, and then you can decompose it. Okay? So this means you wrote. This means if I have one circle action, you can perturb this action so that this becomes transverse, and you can use it after all these things to have a orbit preserving diffeomorphism. Once you have orbit preserving diffeomorphism, you can do the same thing, and you can show that the group is perfect. And so this argument you can use for any manifold times n, which may be not the torus. So on again, some manifold. Thank you. Yes.
Are there other questions?
Yes.
Thank you.
So you don't have condition on the action to be free?
This time, I said for the free action, even if it is free action, you have to do something. And tomorrow, I will look at the spheres. Two spheres, you have rotation, but it has fixed points. And I will explain you how you can do this.
No other questions? If not, let's thank Takashi again.
So